Hey, good morning, everybody. You all seem a little more energetic than you have over the last few lectures. So hopeful that your leaf day that you had on Friday provided you a little bit of relief and that everybody's feeling pretty good right now. And that we're in the home stretch. We have 5 regular lectures to go. The last one will be the review, kind of summing everything up. So that means we have 4 main lectures left. One of them will be the lab Friday, and then the other 2, meaning Wednesday and next Monday, are going to be, we're going to investigate the C++ advanced standard template libraries, kind of give you an idea of how you can use them to be able to solve advanced problems. So this is something you can take further on into your career when you start programming and going into how you can apply what you've learned in this course towards solving advanced problems in your field. But in order for all that to make sense, we have to kind of address 3 main ideas in computational thinking. The first one we've touched on really briefly, but we're going to go into a lot more detail today, is called a finite state machine. So for those of you who have taken logic design, you may know what a Chameleon-Moore finite state machine. You're certainly familiar with combinational logic and sequential logic, but we're going to go over that for everybody so we can make sure that everybody's on the same page. The second one that we're going to go over is an idea called big O notation. And the idea behind big O notation is a way in which we can actually quantify the worst case runtime of a program. And then the third one we're going to go over today is called a Moritized analysis. And the idea of a Moritized analysis is how we consider a scenario in which the inputs and the way in which the user uses our program is not ideal. So the first thing I would like to do is I'd like to take you all the way back to the very first week when we were talking about Turing machines, and I gave you this analogy. I'm going to go over it again. Click, please. There we go. You all remember this? We went over the Notre Dame fight song, if it were actually to play. It decides it doesn't want to. Okay, so, all right, so pretend the Notre Dame fight song is playing. So what would happen is if our video was working properly, what would happen is it would be going through this whole thing where it would be showing, it would be playing this music, and we start the song, and then we play the first 20 notes, right? The first 20 measures. And then what's going to happen is we encounter a particular symbol. Now, for those of you who are not musically inclined, what this means is that at some point, we are going to go back and repeat some music. And this particular symbol means that when we repeat, we go back here. So that starts at measure 21. And then if this were playing, we would say, all right, we're just going to continue to measures 21 to 34. And there's a different symbol, and I want you to notice my use of the word symbol there. At measure 34, that indicates that we have a choice to make. That at the first time we go through, we are going to go back to measure 21. And then the second time we go through, we're just going to keep playing. So we're going to have some sort of decisions that we have to make. So the first time through, we go and we play this small measure 35 and 36, and that takes us back. So that's a and then it gets right in there. And then we play measures 21 through 34 again. And then what would happen is at the end, we would make a decision. Well, we're going to get here, and then we're going to skip measures 35 and 36, and then we're going to play the last 4 measures of the song, that's 37 through 41. And then we are going to indicate that we're done with the song. Right? So the way this is working out is we actually have some sort of decision logic at every stage. And the first stage is what we're going to call combinational logic. Combinational logic, in short, is an idea where you take in some inputs, you perform some operation, and then you put in some outputs. So formally, we're going to say that a combinational logic system has no state present. Therefore, the output is a direct result of a digital system's function. So pretty much anything. So for example, if we have an adder, right? and we have A and B. And we have, for those of you who are familiar, actually we've covered a little bit, we have C in and we have sum and C out. So what's going to happen is there's some sort of logic that goes into determining what there are. So the sum is AX or BX or CN. Once that calculation is performed, the sum and C out are going to go contribute to something else, and we no longer need to keep track of what A and B were. So that's what we say when there's no state present. That means once it's done, it's done. So the question is, well, what happens when we actually need to keep track of things? So for example, that scenario in the Notre Dame fight song, where we went back, we did measures 35 and 36, and then we looped back to measures 21 in order to do a second time through. So how do we keep track of this? And this type is known as a sequential logic system. Oh, I thought I had the sequential. So let me go through and we start here, we start the song, and this finite state machine allows us to determine how each of these things work. If you don't mind, I'm going to press escape because my PowerPoint seems to be struggle busing this morning. I'm just going to, oh, you know what? I see why. Okay, so how about this? I'll just quickly go through this again. And we had this logic. And the whole idea behind a finite state machine is that we have a set of transitions and logic that we make before performing a set of deterministic operations. We are at state 0, we start the song. The conductor comes up, and everybody gets up, and we start playing at the exact same time. And then we play the first 20 measures. So that is another state operation. And so kind of this goes back to the idea of modularity. There are certain tasks, and we're trying to break them down to the simplest logical operation. So in music, you break it down in measures because you want everybody in the band to be able to perform everything at the exact same time. Here, at a higher level, what we can say is we know that before we have all these tasks, measures 1 through 20, and a given state means we can just play those straight without any issue. What's going to happen next is we're going to have some sort of decision that we need to make once we get to measure 20. So at measure 20, we have a different symbol, and that breaks us down into a different logic process. And then we say, well, the first time through, we're going to play measures 35 through 36. And then the second time through, we play measures 37 through 41. And then we end the song. So there's these different tasks that we can go through without having to change the state of the program. So what I have here is what I thought was going to be in the next slide, which is sequential logic. So sequential logic is where we need to save some sort of memory to be able to perform an operation or make a decision later. In this case, for the Notre Dame fight song, we have to keep track of the number of times we've gone through. Otherwise, if we don't keep track, we would just play the song in perpetuity, right? Because it would always be in the first time through. So we have the state, which is our inputs, the current state, and the inputs. So we have to keep track of where we came from. So before, the first time through, when we get to that state of 21 through 34, it came from playing measures 1 through 20, right? So we get there, that's the first time through. The second time through, we came from measures 35 and 36. So we came from two different states when we got to that same place, right? We also had to keep track of the number of times through, which is where we have this input. And the output is the function of the state, which means we have to indicate where we're going next. And we have to update the next set of values. So in that case, when we get to the second time through, we're going to need to update that actual value that's keeping track of that count, so we don't inadvertently keep playing the song forever. And so this kind of uses what's known as a feedback loop. So for those who've taken logic design, you're very familiar with this idea where you have some sort of feedback logic. Maybe you learned about it in SRAM or DRAM memory cells. But the general idea is I perform an operation, but then I need some sort of memory that's passed along in order to perform the next operation with that same logic. And that example is in the right song where we have to go back and decide whether or not we want to perform the measures 21 through 34 and repeat or not. So the first time we go through, we still perform the notes just the same, except we know that the second time through, we would go to a different set of notes. And so kind of getting back here, we now tie this Notre Dame fight song here into memory. So if I'm going through the entire, we start at state 1 and time through, and then I get to 35 and 36. And then when I get through here, I now update it. And now you see that time through has been updated. So once I get here, then I would make that decision on what the output should be. The next state, we now say, function state next will be state 5. And that allows us to get to the end of the song. Okay, does anybody have any questions about this so far? All right, so combining concepts. So this idea of Turing tape, and now you're familiar with the idea of instruction stack and data key. So we have a finite state machine here, but we have a set of operations. And with the Turing tape, we were moving back and forth and performing operations based on the ones and zeros. We now know that in modern computers, particularly the ones on the Notre Dame machine, we have an instruction stack which keeps track of the instructions and the data that keeps track of the dynamically allocated memory. So when you use malloc, new, free, and delete, we deal with the data memory. And here with the instruction stack is basically replicating this idea of a Turing tape. So we see here on the right, we have a set of, we have all the nodes, but those represent the instructions. So the way it would work is we have that program counter that we learned about, and it would go through and we have a memory, a local register that would keep track of what state we're at. And so as I go through, you're going to see that we move up the tape. And then the finite state machine will say, based on this logic, what are we going to do next? We're going to increment the time through. And the first time we would actually go back to a different location on the instruction stack. Now the second time through, do we go to 35 and 36? We don't. What's going to happen is it's going to move up to the instruction stack. And then we get to the sum, and that is where we would do our return to 0. So this allows us to kind of combine several concepts together. How can we perform this operation where we're doing several things simultaneously, and we have to make several decisions? By writing it in this specific way, you can reduce the amount of code that you actually write. So instead of having to write that same set of notes twice, we just do it once, and we use these symbols to be able to indicate when we want to go back. Likewise, here we have what you're, especially if you go on to like a computer architecture course, for those of you who might be taking more computer science classes, use assembly level languages that tell us precisely where to go onto the instruction stack. So to formally define a finite state machine, there are several definitions that I want to take you through first. The first one, which you're familiar with because I've been kind of describing them, are the states. These are where we perform concrete, definite, discrete operations. And these are the finite set of states in the finite state machine. And so the emphasis is on the word finite. We have a finite set of operations that the computer can perform. And going back to the Turing analogy, that finite set of operations that can be performed by a computer were in that book that was used by the man inside the box. So basically what you're doing is you're building a set of operations that ultimately builds upon that base set, which you've learned about addition, subtraction, multiplication, performing dynamic memory allocation, and everything else we've learned with classes and objects and inheritance and polymorphism all builds upon these fundamental ideas. The second thing is an alphabet, which is a non-empty set of symbols indicating intended use of operation. So this is why you saw me using the term symbol over and over again, because a symbol in the alphabet dictates what we want to do. In most computing finite state machines, the alphabet is going to be zeros and ones. And this will dictate logic about what it is that we want to do. So if it's 0, go to this state. If it's 1, go to this state. In the Notre Dame fight-song finite state machine, we broke it down to numbers corresponding to the states. We have state 1, 2, 3, 4, and 5. And so we have numbers in our alphabet. And then, based on that, we use these to make decisions. And that's why we're going to talk about an input alphabet versus an output alphabet. If you remember when I was talking about Turing machines at the beginning of the semester, one thing I really wanted to drive home was this idea that when we type into the computer, it doesn't understand what we're doing. And then when it's printing something else, the computer doesn't actually know what this is. It's just printing in ways in which we understand. So tying back this into the way in which you program, you have to be mindful of how what goes into your program and what comes out of your program. So the input alphabet is going to be the set of symbols that are interpreted by the machine, and we use sigma to represent those. And the output alphabet is the finite set of characters interpreted by the user, and that's represented by L. Does anybody have any questions before I continue? Let me check the chat as well, see if we got any questions in there. All right, so sorry, I skipped a step here. So now we have transition functions and output functions. Transition functions are where we determine what the next state is going to be. And the transition functions are based on the input. So in this case, so for example, we are currently at the state in the finite state machine. I'll go over this in more detail on the next slide, where we are playing measures 21 through 34. We make a decision based on the input. In that case, the input is the time through. So the transition function says if we are at state 3 and the input is first time through, we go to state 4. The other transition function says we are currently at state 3 and we're the second time through, then I decide what it is we're going to do on the output. So that's the idea of the transition function. And the output function, it maps the part of a state and an input to the corresponding output symbol. And in the Notre Dame fight song FSM, the output is music. I go to a certain state, I say I play 21 through 34. What's coming out is what we hear. Okay? And so the music, unless your laptop decides it doesn't want to play the song, what you'll be able to hear is the output function of the finite state machine. So we map a pair of states and an input symbol to the corresponding output symbol. So in this case, our input symbols are states and notes and symbols that tell us whether or not to repeat what notes we want to play at certain different times. And the output function is sounds, anything that we can hear in order to be able to interpret that as music. All right, so the whole Notre Dame fight song, we have these states. There are 6 states in the machine. That's notated by S. The sigma, input alphabet, notes, symbols indicating repeat and skip. The transition functions tell us where to go along the sheet music and how that corresponds when breaking it down to zeros and ones, help us dictate where we would need to go on the Turing tape or the instruction stack. The output alphabet is the musical sounds you hear, and the output functions are the notes being played based on the current state. So what I would like to cover next are 2 main types of modern finite state machines. So they were invented about the same time in 1959, And as most things were, 1959, if you go into, take my data structures class, for example, I go into a little bit of detail about how a lot of these modern data structures were invented in the late 50s and early 60s to try to figure out the best way to shove computers onto a rocket. And we had to make things really small and efficient because the more the computer weighs, the harder it is to get the rocket into space. So 1955, George Mealy, he invents what's known as a Mealy machine. And the whole idea is that the output values are determined by both its current state and its current inputs. So what we have here is we have a set of inputs, and we have combinational logic, and we have states of registers. Now, based on what we put into the register, we have an input here from the value and the current state to determine the next state. So those outputs are determined by both the input and the value from the state. And I'm going to go over an example that will hopefully clarify in the event that's a little confusing, because it can be very confusing the first time you kind of see this. But the general idea is that I have a state, and that state is going to produce some sort of output, and then the input and that produced value are going to tell me what the output is going to be. All right, so here is an example of a Mealy machine. So in this machine here, we have 4 states, and each of these corresponds to a current state, an input, and the output. So what's going to happen is the input is going to tell us where to go, as well as dictate what the output is going to be. So let me give you an example. Let us say that we are currently at state 1, 0. The way this notation works, so I have it notated here if you want to review later, the left is going to be the input and the right is going to be the output. So here, from state 1, 0, we have 2 output arrows. I'm sorry, here's the other one. The first output arrow is 0 and 0. So what that means is that if we are currently at state 1, 0, and we receive an input 0, that means we are going to go to state 1, 1, and our output is 0. Input, transition, output. So the input not only contributes to where we're going to go, but also to what our output is going to be. Likewise, if we are at state 1, 0, and the input is 1, that means the output is 0, and we go to state 0, 1. So this is why we define this as a Mealy machine, because the transition contributes to both the output and the next state. Yes. Sure. All right. What specifically would you like me to? Sure. Okay. So let's start at 1, 1. Okay. So what's going to happen is I can choose my input alphabet is a 0 or 1. My output alphabet is also 0 or 1. If I'm at state 1 1, then I have 2 output transitions. This way and this way. Does that make sense? So the top one is 0 0. That means that if the input is 0 and I'm at state 1 1, then I transition to state 0 0 and my output is 0. Likewise, if I'm at state 1 1 and the input is 1, then the output will be 0 and I will go to 0 1. Did that clarify? We're going to go over a whole example problem in just a moment too. Yes. All right, how about this? I'm going to go through the example question, And what I want to do is I want everybody to tell me what they think is going to happen. And hopefully I think that this will clarify both of your questions. I think that'll be the most efficient way. All right, so what I'm going to do is I have a set of inputs, 1, 0, 0, 1, 1. And we're starting at Q1. So that we're going to solve that. We're going to start here. And what I'm going to do is I'm going to walk through the first set of decisions. And then what I want everybody to do, and I'll bring up the chat as well so everybody who's online can contribute as well. We're going to walk through and do all of these inputs and see what the whole operation is. So we're going to start at 0, 1, right? And the input is 1. Does everybody see that so far? Input is 1, output is 0. Then we go to S next, and S next is going to be 0, 0. All right, so we're currently at 0, 0, and the input is 0. So what do you think? So somebody take a guess as to what they think is going to happen next. Yes. Absolutely right. We have 0 as the input, 1 is the output, and we go to 1, 0. Yes. 1 is the output because we have this 0/1. 0 is the input and 1 is the output. That is the notation. Zero, it's along the notation is along the arrow. Here, let's try another one. Okay, so we're at 1, 0. All right, so the input here is 0. So somebody tell me what they think is going to happen. Yes. Very good. So here's 0, 0. And what we do is we go along the specific edge to the output. So there's an arrow from 1, 0 to 1, 1. Right? And what happens is there is a notation along that edge that says 0/0, which means if the input is 0, I will go along this edge, and then the output will be 0. All right, does that provide clarity? Awesome. So now we're here. So now we have an input of 0. So what do we think is going to happen here? Somebody else. I saw several hands up. Yes. Very good. All right, so we have 2 more. Let's take this home. Who else wants to give it a try? Somebody from over on this half of the room, Yes. The input is 1. Very good. All right, so now we're at 1, 0, and the last input is 1. Yes, in the back. Yeah. Mm-hmm. All right, so the states are listed here in binary. So 0, 0 is 0, 0, 1 would be 1, 1, 0 would be 2, and 1, 1 would be 3. Does that clarify your question? Those are the state values. So remember how I was saying state 1, 2, 3, 4, and 5? They're just notated here in binary. Okay, did that clarify? Okay, yes. They are arbitrarily chosen by the program. Yes. Well, ultimately, the output numbers are chosen by what the program needs to do. And I'm going to show you an example in a moment. But basically, it's, ultimately, these are output tasks, and this is a simplified version to clarify on binary results. All right, so we got one last one. So we're here at what, 1, 0, and the input is 1. So what do we need to do? Yes. Very good. So input, we have 1, 0, and then the output goes to 0, 1. Okay, so the thing with Mealy machines is that they can be a little complex. The input-output notation can cause some issues, as we saw from the questions. So Edward Moore comes by in 1956 and says, well, what if I just say that the state that I'm at has the output, and the input just tells me where the next state's going to be? Let's cut, I may need a few more states, but let's cut out the middleman. Let's out this transition idea. And all we're going to have is when I get to state Q0, Q0 does something. Then I go to state, that makes some sort of decision. When I get to state Q1, that does something. So 0, 0, 0, 1, 1, 1, 1, 0, or whatever it happens to be. And that just gives me my transitions and my output logic. So here is a Moore machine. And so here we have Q1, and it says 0, Q2 with a 1 inside, and then Q3 with a 0 inside. And so here we have a set of inputs, 1, 0, 0, 0, and 1 with an initial state. I say 0, 1, but here we're going to call it Q1. And so let me walk through the first step, and then we're going to walk through the rest of this Moore machine. So Q1, we're going to start here. The input is going to be 1. And then we get to Q1 here. So the value inside is 0. So that would actually be 0. Does that make sense? So when the next input is going to be 0, so what do we think is going to happen? Yes. Absolutely right. So we would go to Q2. Right there. So now we're at Q2 and the input is 0. So what do I need to do? Someone give it a try. Yes. Absolutely right. So now we're at Q3. The input's going to be 0. What do we need to do? Yes. Very good. So go 0, we're back to Q2. So Q2, we have 0 one last time since we've solved this one. And now we're at Q3 and the input is 1. So what do we think we need to do here? Yes. Very good. A lot simpler, right? A lot fewer questions. That was Edward Moore's goal. So based on these two finite state machines that we've looked at, which type do you think this Notre Dame Flex song FSM that I've been presenting is? Yes. Okay, so we have a theory that it's a Moore machine. So everybody was about to raise their hand? Is everybody in agreement, or do we have a dissenting voice? Okay, a lot of thumbs up. So you are correct. This is a Moore machine, and the reason why, the output is the same every time we hit the same state. We know that the outputs are determined by its current state only. That's part of the definition of the Moore machine. So there it is. It's a Moore machine. So if we break it down, we can change this from tasks that we want to do to some sort of naming notation. So here I'm just naming it in binary. This is arbitrary and this is what I've chosen. So then here I would break this down. We want to break it down to the formal definition. So we have states 0, 0 through 0, 5. The input alphabet, it would be 0 or 1. So there I'm just saying we're going to do the same thing. And the input alphabet is whatever the, whichever time through would be. So 0 would be the first time through, 1 will be the second time through. And then we define the arrows define our transition functions, and we have our transition outputs, tell us what we would do at any given moment. So that's what we would be using, play these certain measures, play these certain notes. And then the output alphabet is the set of all possible musical notes. And so what I'd like to do is I'd like to show you a little bit. I put it into code to kind of combine some concepts that we've had. So this is in C++, and I'm going to say while the state is not equal to 5. So I have two values that I'm using to keep track of. I have time through and state. And so what's going to happen is I use a switch statement. So switch statements are quite helpful in state diagrams. And it actually kind of makes sense when we think about it, because switch statements require deterministic values, right? We had to use unsigned ints, long unsigned ints, chars, anything that could be defined Exactly. We couldn't use doubles or floats. And so with case 0, I just print out begin song and I say go to state 1. I'm at case 1 and then I would print out play measures 1 through 20 and go to state 2. In case 2, this is where I have to make some decisions. So I'm going to say play measures 21 through 34. Now, if it's the first time through, and that's notated by time through equals 0, then we set time through is equal to 1, and I go to state 3. Otherwise, I say second time through, don't repeat, and we go to state 4. At state 3, I say play measures 35 and 36 and go back to measure 21. And then I set the state equal to 2. Then case 4, I can play measures 37 through 41. I'd say state is equal to 5. And then case 5, I'd say end of song, state is equal to 6. And that's going to help us out here because once state is equal to 6, that breaks our while loop condition. And then I have a default case there to say it's an invalid state. So what I'm going to do is I'm going to run make nd fight song FSM. And then just by using where we start and how it's going through, it runs the entire program for me. Does everybody see that? The next thing I'd like to show you, so there's the code I just produced, is that I have represented this more machine in C++. And so what we're going to do is we're going to generate this exact output. We're going to do 1, 0, 0, 0, 0, 1, and I'll produce the outputs based on what those values should be. And so what I've done is I first, in more.cpp, to review, I'm going to print the output. And what I'm going to do is that each time through, I'm going to put the value that's inside of the state, I'm going to push it back onto a vector. And what's going to happen is I'm going to print out the output when we're done. So I'm going to iterate through, and we'll do it like this. Inside main, what I have is I have char input char 0 and unsigned int state. And then I create that vector to store the outputs. And so with a while loop, I'll say, well, while input char does not equal 2, so I'm going to either say 0 or 1 with a valid input, and now use 2 to end the program. Then what I'm going to do is I will go through, I'll say input 0 or 1 for the next state, and then the usual input using standard CN. And then if the input is equal to 2, then we're just going to break the while loop. Otherwise, we have our switch cases. So Q1 is going to be case 0. And so hopefully this clarifies some of the questions that were from earlier, that we're relating characters to our specific states. So we can name them arbitrarily based on what we're trying to represent in code. So I'll say input character is equal to, if the input character is equal to 0, I'll move to state 1 and I'll push back 2 onto the output vector. Otherwise, I'll go to state 0 and I'll push back 1. Case 1, Q2 is 1. So if it's 0, I go to state 2 and I'll push back 3. And then state 0, I'll push back 1. And then the other case is just the arrows as well, pushing back 2 if the input is 0, and if it's 1, we'll push back 1, like so. Yes? Those are the specific state Q1, Q2, and Q3. And so what's going to happen is when I run make more, what I can do is I can run this and I can just test our knowledge. So if I say 1, 0, 0, 0, 0, 1, and then 2 to end, I'll say I'll start at Q1, Q2, Q3, Q2, Q3, and Q1, which is precisely what would be produced. And you can use this to do whatever you want. So you can do 0, 1, 1, 0, 1, 0, 2. And it tells me what the output's going to be. All right, so does anybody have any questions? You click through this. So here's the slides for the code, so you can review it later if you like. Does anybody have any questions before I spend the next 10 minutes going over this idea of big O notation? Yeah.
So that program you just ran with the normal machine, was all that specific to that triangle?
Yes.
So, but a normal machine could have different triangles.
Absolutely. So you can design it. So a very common program, and in fact, this is something you will write. A very common program to test your knowledge of finite state machines is to run a program that simulates a code machine or a vending machine. You put in a certain amount of money, and then based on a certain amount of money and what the user has input, you can get certain things out of the machine. So finite state machines on all of those vending machines on campus.
Yep.
Any other questions? Let me check the chat, see if there's anything in there. Okay, so to understand some of the things that we're going to go about, we're going to do like a brief survey of things like trees, dynamic arrays, vector you're already familiar with, and how to implement certain algorithms. We need to be able to quantify how fast something runs. So the way that we do this in computer science is called big O notation. And the general idea behind big O notation is we use it to be able to define what we're going to call the upper bound of a set of functions. In short, we're going to come up with a way to say that this is the worst possible runtime for a specific program. And that's good because this gives us a worst case scenario based on certain factors. So one thing we're going to be thinking about in a lot more detail is what happens when a user doesn't do precisely what we want them to do. So first I want to formally define big O notation, and then we're going to go over a couple of problems. Big O notation, we say that for a function g of n, we define, for a function g of n, we define big O of g of n as the asymptotic upper bound for the set of functions. And in a formal definition, we say big O of g of n is equal to f of n, where there exist positive constants c and n initial, such that 0 is less than or equal to f of n, is less than or equal to c times g of n for all n greater than that initial value. And so what I want to do is I want to go over an example that makes that potentially gibberish sounding equation make sense. I'm just giving everybody a split second to finish writing notes. Okay, so let's take a look at this code segment and then apply what we're going to calculate to this big O notation equation. So here I have a for loop where I go from int I is equal to 0, I is less than m, I plus I, and then inside that loop, I have a loop that goes from j to array length, and then inside I do k plus equals array I of j, array I of j. And then outside that loop, I have a while loop where while m is greater than 0, m divided by equals 2. Does that make sense to everybody? So here's what we're going to do. We first say, well, inside of that for loop, we have some sort of addition. And we know that with this double array, we're basically doing array arithmetic and array arithmetic. So no matter how big these two values, I or j, are, we perform two additions, right? So that's how we understand pointers. So that means we're going to perform two additions to get the value of array ij, and then we store that value in k with a plus equals, so it's three additions. When something works in constant time, no matter what the inputs are, we say this is, we're going to call this big O of 1. But for right now, we just say it's 3, so we're going to put O of 3 inside there. Does that make sense to everybody so far? The next thing we're going to do is we are going to go to the for loop. So no matter how many times we perform this operation, we're going to loop this array length times. Does that make sense? So the number of operations that we're going to have is 3 times array length. And then outside of that, what's going to happen is no matter how many times we do this, whatever n is going to be, we are going to say it loops through m times. So the total result is going to be 3 times array length times m. So that's what I have in red there. So the reason why this approach is beneficial is we don't know what array length is going to be, and we don't know what m is going to be, right? So what big O notation is we assume the worst case scenario. M is bad, array length is bad, right? And so what we're going to do is we're going to say we're going to come up with a variable that represents the worst case for all the variable values, and we're going to call that n. And so therefore, when we plug this in, we would say 3 times n times n. Now, this last part here is actually going to be really helpful for you as you go on in your career. Let's say n is 64. So if I want to go through that, it's going to be 64 divided by 2 is 32. 32 divided by 2 is 16. 16 divided by 2 is 8. And we would go through that 6 times. 128, we would go through that 7 times. 5, we would go through that 32. This idea, when you're dividing something, we say it's log base 2. Because the number of times it would take to divide by 2 to get through this program. So we would say this is log base 2 of m. And so what we will do in the big O notation is replace array length m and m with all of them with n, which n represents our worst case scenario. So then, like I show here, the worst case scenario, we now have 3n squared plus log base 2 of n. That's going to represent what we call f of n in that notation. And so now we can see that we have some sort of constant in front of it, right? 3. So that's where that constant c is going to come into play. So what's going to happen here is I'm going to try to come up with some value for g of n that is always greater than or equal to the equation that we derived. So in this case, I have 3n squared plus log base 2 of n. So if I set n is equal to 1, we know that log base 2 of 1 is equal to 0. So if I set 3n squared plus log base 2 of n, where n is equal to 1, that's going to give me 3 times 1 squared plus 0. And c here, I could say, well, for all those values, let's say I set c equal to 4. In this case, 4 times g of n, and I'm going to pick n squared here, will always be greater than 3n squared plus log n, no matter how big n gets. And so therefore, this big O notation will be, so kind of tying this in, this is a good place to end the lecture here, is that we're going to say that for big O of g of n, we're going to say g of n is n squared, such that for the equation 3n squared plus log base 2 of n, g of n times 4, which is the value c, plus is going to, for all values greater than or equal to 1, we know that 4 times n squared is the worst case runtime for our program. And so therefore, what's going to happen is in the bingo notation, we would take out that 4 because that's the C. And so therefore, we say that this program runs in bingo of n squared time. Does that make sense? And so I will just very quickly click through this one just to show you my approach. And this is where we'll conclude lecture. So here I have some value k divided equals 3. So this would be log base 3 of k. And then outside it's 2 times m. So it's 2 times m times log base 3 of k. And so plugging in n, I get 2 times n times log base 3 of n. And then trying to find that c, I could actually make it such that c is equal to 2. So therefore, I would say g is n times log base 3 of n. So in this case, it's easy because 2 they're equivalent equations. So now I can say that c of n and n is n of 0 being 0, that this program will always run in n times log 3n time, no matter what the inputs are. Right, does that make sense to everybody? I have a question about asymptotic analysis in the homework assignment. I'm going to take it out as soon as I get out of my data structures lecture. So once that's done, I'll send an email out to let you know that the homework assignment has been updated appropriately. On that note, it is time to go. So if there's no other questions, you're dismissed.